Okay, hi everyone. Today I'm going to attempt Codeforces round 686 division 3. And as you must have seen in the title as well, this is an English video. This is, I think, my first English screencast. So before the contest starts, which is in 2 minutes something, first I would like to talk about why I'm doing this video in English. So first of all, at some point I have to do at least some content in English, and this doesn't mean that I'll eventually be shifting to completely English, which might be possible, but this doesn't mean that. And the reason I would be doing some English content is because like I want to put my streams here on this Codeforces sidebar, and I don't think like local languages should be there because they won't be relevant to a lot of people. So that's why like I have to do some content in English at some point. So this screencast is kind of like a practice screencast so that I can see if I'm actually comfortable with doing English or not. And I picked division 3 specifically because the division 3 is first of all less significant, I mean less relevant to a lot of people because it's not rated for 1600 plus. So it's relevant to a smaller audience. That's why if I want to do some kind of experiments, this is the best place to do them. And apart from that, actually Div 3 contest requires some less thinking. So like I have more time to think, and I would have to think less and speak less and things like that. So that's why I picked this contest as my first contest for the English screencast because I mean if I had picked the Div 1 or something, I didn't want to spend majority of my attention towards translating whatever is in my mind because a lot of times I think in my regional language. And so that's one thing. And lastly, I won't be attempting the entire contest because I have an exam today actually. I have to submit by the midnight or something. So I won't be attempting the entire contest. It will be like 1 hour long. So I mean, this is not a one of the state of the art videos that I have on my channel. So that's why I thought if I want to experiment, I think this is the best video to experiment. So cool. The intro was exactly as long as needed. Now the contest has started. Let's move on to the first question. Okay, special permutation. You are given one integer n. Recall that a permutation is the length of array n such that distinct integers from 1 to n are in arbitrary order. Okay, so this is an example of permutation. Your task is to find the permutation of length n such that there is no index I such that pi equal to I. Okay, so they just wanted derangement. I think one cyclic shift should be enough. Okay, so okay, they have given an n, and there are test cases. Then I input n, right? 1 minute. What do we have to output? Okay, yeah. So now we take n, and we'll just print one cyclic shift of this. Okay, so first of all, we'll just print 2 to n, and in the end, we'll print 1. So this will always work. Yeah, so this pattern will always work. Now I will submit this answer. Right. Okay, that was correct. But 1,000 other people also did it, so that was not a big deal. There's a game called Unique Bid Auction. Okay, we can read about it. So we'll read it later because that will only waste time in the contest. The winner of the game, the participant, the number he chooses unique and is minimal. Okay, right. Yeah, I've heard about those games. I mean, at 1 a.m. or something in the night, there were those kind of bids. Like you have to place the unique minimal bid. The task is to find the index of the participant who won the game or -1 if there is no winner. Okay. Okay, so all the bits are given, and we have to find the index of the person with the lowest bid. Okay. So what I will do is I will store the frequency of all the bits, and yeah, I think that's enough. I will just store the frequency of all the bits, then I'll iterate the uh, no, wait a minute. Um, okay, I'll keep pushing the bits and their index into a set, and whenever mm, mm, like whenever there's a duplicate, I'll remove them, right? Or I can just sort them. Yeah, that's better. So I'll make the pair. I'll make a pair of the bid and the index, and then I'll sort them. Then I can easily find the first unique bid. First unique bid, right? So let's try this. Okay. Test cases. Now I have n. Then I have the array, right? Let's make pairs because I want. Okay, so okay, so I made pairs of the bits, comma index, the vector, and then I sorted it. Now it's easy to find the duplicate. Okay, so I have to find the first duplicate, right? Now if okay, n can be 1, right? Okay, wait. So if n is equal to 1, then it's trivial, and the answer will be always 1. And that's it. But if it's not 1, let's see if 1 is the correct answer or not. So if like I can put it here only. Otherwise, if um, okay, wait a minute. So in the sorted order, let's see if the first bit is the correct answer. So if a0.fr is not equal to a1.fr, then that means the first bit in the sorted order is the correct bit. So the answer will be a0.sc, and yeah, I'll leave a new line. Now I have to check just the bits greater than 1. So from 1 till n, I'll run this route. Okay. Now if okay, so if like nothing works out, then the answer is -1. So I'm just gonna write it, and if I find the correct answer, I'll just return. So if ai dot fr is not equal to a of I minus 1 dot fr, then see out ai dot sc, and that's it. This should work. Wait a minute, what happened? Oh, sorry. This loop should have been from 0 to n. Okay. Oh, my compiler is doing some kind of problem. Wait a minute. I hate it when it happens during a contest. Actually, I have some problem with the compiler. This looks okay. Why isn't it running? Okay. Okay, this seems wrong, I guess. Oh, right. Yeah, this is wrong. So it should it should not be equal to both of them, right? Um, and it should not be equal to the next one as well. Okay, if it's not equal to both of them, then it's the answer. But now I have to manually check the last one as well. So if a of n minus 1 dot fr is not equal to a of n minus 2 dot fr, then the answer is a of n minus 1 dot sc. Obviously, I'll print a new line and edit. So there were some cases for the endpoint of the array. Okay, now it's correct. Green means correct, and my answer is correct. Now I'll submit. I think I spent a lot of time on this. It wasn't necessary to spend this much time here. Anyway, okay, at least we got accepted. So now I'm at problem C. You are given a sequence A consisting of n integers. You want to transform the sequence so that all elements are equal. To achieve this, you choose some integer x that occurs at least once, and then perform the following operation any number of times, possibly 0. Choose some segment LR of the sequence and remove it. But there is one exception. You are not allowed to choose a segment that contains X. Okay, so I'll choose X and then I'll remove a segment that does not contain X. Okay. Okay, I can remove any number of segments that do not contain X. Okay. More formally, you choose some contiguous subsequence, then none of them are equal to X and remove it. After removal, the numbering of the elements, right, changes. Okay, yeah, they will. I mean, they will merge when like you will remove the part that you cut out, and then you'll merge the remaining parts. So the indices will change. For example, okay, the indices will change. It's fine. Note that choosing X is not an operation. Also note that you cannot remove any occurrence of X. Okay. Your task is to find the number of operations required to transform the sequence in a way described above. Okay. So what do we have to do? Okay, my task is to make all the elements equal. So right, what I will do is I'll choose X and then I will try to make all the elements equal to X. Right. So yeah, okay. I think I can try out all of the values that are present in the array, and what I want to do is whenever there is a let's say there are three fours in the array. Actually, I'll just explain. So, like let's say the array is something like this. Okay. So there are three blocks where there's no four, and like we have to convert those three to four. Like all of these, we'll have to convert to four if we choose x equal to 4. So this is what we have to do, right? And to make things easier, I think it's always beneficial to assume that there's a 0 at the end and a 0 at the starting, and both at the both ends there is 0. Actually, no, I think it's always beneficial to put x at both ends, right? Now we just need the gaps between the x, between all of the x. But if there are two continuous, then we don't put them. So yeah, it can be done easily. Okay, let's see. Mm, okay, so let's see what we can do here. Right, so first of all, I have to take the input. Okay, now let's see. The minimum number of operations required to transform the given sequence, right? So I will try each element in the array, and for that I think I need this. Okay, let's keep a vector of all the indices where the elements are present. Wait a minute. Okay. Now in this I will keep the indices of all the elements. So for each test case I have to clear that. Okay, I'll just clear it. Cool. After clearing, I'll put a 0 and a n here. Okay. Okay. So I'll put a 0 and in the end I'll put n plus 1. Okay. Uh, Assuming that the indices are 1 based. So like right now I put a 0 and in the end I'll put n plus 1. Okay. So okay. Now let's say I have a variable. I have to take an input. Okay. Mm, Wait, so what I will do is I'll just push that back into this vector of indices. Mm, what I should do is vx dot push back I. I'm pushing the indices. But there is one exception. Let's say the last element in the index was already equal to x, then like I should remove that first. So if vx dot back equal to I minus 1, then I should remove this. Then I should do vx dot pop back. Okay, so now this should work. And finally, I push n in all of them, just like this. So point I equal to 1, I is smaller equal to n, and I plus plus. So at all these places, I will push n plus 1. So vi dot push back n plus 1. But then again, there's this exception. So if vi dot back is already equal to n, then we'll just remove this first. Vi dot pop back. So this is correct. Now we have to count the number of operations, right? So so I'll just take all of them. Cool. I'm trying each value if it's equal to x or not. Like if I take this x, what will be the answer? So let's say answer is infinity. I'll try to minimize it and then I'll bring the minimum answer that I can get. Okay. So yeah, the number of operations required are just equal to the size of the frequency vector minus 1, because if there are two elements in it, that means yeah, if there are two elements in it, then that means that I can perform a single operation and do it. So if there are k elements, then I can perform k minus 1 elements. So the answer should be the size of the frequency array minus 1. But there is one exception. If size of the frequency array is 2 and Vx0 is equal to 0 and Vx1 equal to n plus 1. So this is an exception because this means that the element x is not occurring in the array. So here I must continue. And in rest cases I can do this. I think this should give the correct answer. Okay, so green means it was correct, and yes, it was correct. So let's submit this. I don't think I did something wrong. It should be correct. Oh, it was wrong. Okay, so let's try to figure out where we went wrong. Yes, clearing the vector. The values of AI are bounded by n, so it's sufficient to clear only 1 to n. It's sufficient to check only 1 to n. Hmm. Why can't we remove all of the elements? Okay, I think it's not allowed, otherwise the answer here would have been 1. Okay, but it is 1, right? No, the answer here would have been 1 if we were allowed to um, print the empty array as an answer. Okay, let me see. So what I counted was non the number of non-contiguous occurrences of the number of contiguous segments that are present in the array. Something like this. Excuse me. So for each element, I counted something like this. Like there is this, and here was also 4. Here was also 4. I kept this one, but I didn't keep this, and I kept this. So to convert all the entire array to 4, I will have to pick this, and this, which is exactly equal to 4 minus 1, and that's 3. So I think this is correct. I don't know why it's not working. This means it should work, right? And it's not a time limit exceeded, it's a wrong answer. Okay, did I write this condition wrong? No, but this necessarily means that there are only 2 elements in the array, in the frequency. There are only 2, and one of them is the 0, and the second is n plus 1. That means the element didn't occur anywhere in the array. Oh, no, it did occur. Okay, I shouldn't check it like this. I should just keep a set instead. So if not s dot count x, I'll continue. I'll keep a set, and I'll just insert that element into the set. Sorry. Okay, now it should be correct. Okay, so we made a mistake, but I think this time it will be correct. Okay, yeah. Okay, so we're not doing good so far, but doesn't matter because it's not rated for me. Now you are given an integer n. Your task is to find a sequence of integers such that each ai is strictly greater than 1 and the product of this sequence is equal to n. Mm, we have to choose a sequence of length k such that its product is equal to n. Okay. ai plus 1 is divisible by ai. Okay, cool. Mm, k is the maximum possible. So we want such a sequence of the longest length. If there are several sequences, any of them is acceptable. It can be proven that at least one valid sequence always exists. So what is the input? Okay, we are only given n, and that's the only input we have. Okay, so we have to take all of the divisors of n. Okay, and the product should be equal to n. Mm, I think we can do it using the prime factorization of n because yes, it should work using the prime factorization. Let's say n is even. Wait a minute. Uh, it's something like let's say I write n equal to its prime factorization, so it's like p1 to power a, p2 to power b, and so on. Then what I can do is the first number can be 1, right? First number of the sequence. Okay, each ai is strictly greater than 1. Okay, so the first element can be 1. So the first element has to be at least one of these primes. And, the first element has to be equal to at least one of these prime numbers, right? So mm, let's say I pick the first number p1. Okay, then the next element should be p1 into something. Then the next element also should be p1 into something, and so on. So what's happening is that like when I will multiply all of these, let's say if there are k elements, so I will definitely have p1 to power k, right? So if I will have p1 to power k, we can keep equal elements, right? Ai can be equal to a plus 1. Yeah, yeah, because it's not mentioned anywhere that we can't. Wait a minute. Yeah, we can keep equal elements where they are increasing. Um, so anyway, so if we take k elements, it will be equal to p1 to power k. So for the answer to be, wait a minute. For the answer to be k, at least one of the prime factors exponent must be greater or equal to k. That means at least a is greater or equal to k, or b is greater or equal to k, or something like that. So let's say a is equal to k. So I will keep p1, right, for these k elements. But what I will do with the rest of the prime factors, with p2, p3, and p4, etc. So I think if they are less than k, I can just adjust them somewhere. Like let's say if k is 4, so I will keep 4 p1s, right, in a sequence. Then if b is equal to 2, then I will keep 2 p2s, and this way I can accumulate the entire number. Okay, so what I need is just the prime factorization of the number. Okay, so I need the prime factorization of the numbers, and I need it quickly. I can find the prime factorization in square root n, right? So should I trust this? I think I can trust that because I think I can naively find the prime factorization, right? Because it won't exceed 10 to power 5 for a single test case. And even if there are 5,000 test cases, it won't matter much. It will just be equal to 5,000 into, I think, 10 to power 4 or something. It should work. So yeah, I can naively find the prime factorization. Let's see the number of submissions. Okay, they are quite a lot. So yes, we can naively find the prime factorization. And I think that's it. That's all we have to do here. So yeah. Now I need the prime factorization. So I keep store the prime factorization as vector of parent. This will be equal to the prime number comma the frequency. Now n can't be 1, right? So for int I equals to I smaller I into I is smaller equal to n I plus plus. Okay. Now I can say that p equals I if n mod I equals it's not equal to 0, then I will have to continue. But if it is equal to 0, I will keep a count of how many times it can divide. So while n mod p equals 0, I'll do n divide equal to p count plus plus. Okay. Now there's no occurrence of p in n, so I can just store it in the vector p comma count. Cool. In the end, if n is not equal to 1, then I'll say there's another prime factor, and that's n itself, and its frequency is 1. Okay, so now I have the entire prime factorization. I want the maximum one, right? I think I'll have to sort these according to the frequency. So I think I should keep the frequency first and then the count. Sorry, the frequency first and then the actual prime number. Cool, this is better. Now I just have to sort them. Sort all three. And I have to sort them in decreasing order of frequency. So yeah, I'll just sort it and reverse it. Okay. Now let's say the number I will print is equal to 1 in the beginning. So what I will do is for int okay, so sorry, for auto x in v, I'll keep multiplying the second of this. First of all, the answer is equal to v0 dot fr. This is the maximum frequency, so this is the answer, and I can just print it right away. See out answer. Okay. Now the numbers I will print are in such a way that like the like all of the k numbers should have the one with the maximum frequency. In fact, let's try to just print k numbers. Print I equal to 1, I smaller equal to k, I plus plus. Okay. We don't have to reverse this actually. We can just take the last element instead. Okay. Now let's say I'm printing PR every time. I'll just have to change PR accordingly. So if v dot back dot fr okay, plus I equals answer, then I think I can include it in this PR into equal to v dot back dot sc. Then I'll just pop it back. And I think this should not be if, this should be a while, but I have to make sure v is not empty. Not v dot empty. I think this should work. No test cases yet. Okay, I think I did something terribly wrong. It didn't even run. Something must be wrong here only, because yeah, it was. So while it's not empty and the last element frequency plus 1 equals answer. Multiplying the second element and how can this be wrong? I mean, is it giving a... Oh, sorry, this should be and instead of or. Right, sorry. Yeah, let's see if it's correct. So 2, 6, 30. Do they multiply up to give 360? 30 into 2, 60, 60 into 6. Yeah, correct. Are all of these correct? Okay, these seem correct. We might get it yearly, but I think that's very unlikely because we have 3 seconds and square root n is not a lot. This should work, I guess. Okay, yeah, it was correct. So I don't think I will be doing F in this contest. I'll just do till E and finish the video because, as I said, I will stop the contest after 1 hour and we just have 24 minutes left. And I don't even think I can solve E in 24 minutes. But even if I'm not able to solve it, I'll complete this before stopping the video. So like if I take 30 minutes, I'll extend the video a little bit. So you are given an undirected graph of n vertices and n edges. And vertices and edges, it is guaranteed that the graph is connected. Okay. There are no self loops and multiple edges. Okay, it's a simple graph. Your task is to calculate the number of simple paths of length at least n. Sorry, and length at least 1 in the given graph. Now that the paths differ only by their direction, considered the same. That is, you have to calculate the number of undirected paths. For example, paths 1, 2, 3 and 3, 2, 1 are considered the same. We have to calculate the total number of paths. Okay. And 1, 2, 3 and 3, 2, 1 are the same. Recall that a path. Okay, so recall that a path in the graph is a sequence of vertices such that each pair is adjacent. Okay. The length of the path is the number of edges in it. The simple path is a path such that all vertices are distinct. Okay, all vertices are distinct. So what we can do here is we can kind of impose a partial order to all this. So to avoid recounting, like to avoid counting both 1, 2, 3 and 3, 2, 1, what we can do is we can only count paths such that the starting is smaller than the ending. So this way we will get only, let me think. Yeah, I think, yeah. This way we will only get the paths once. Also, we can just count all of the paths and then divide them by two, because uh, yeah, each path will appear twice. So we can pick one of these two methods, and now we have to calculate all of the paths in the graph. So let's see what we can do. Actually, there's one thing. There are only n vertices and n edges. So this is like, I think instead of giving m edges, which is m is like instead of giving a free variable m and giving m edges, they gave us n vertices and n edges. So I think there is some hint there. Maybe if maybe it's easier if it's n instead of m. But I don't think that's okay. It is guaranteed that the graph is connected. Right. Okay. Okay, yeah. So definitely this is a big hint. And the hint is that, okay, I'm going to tell what the hint. So we are given a graph of n vertices, and there are n edges there and the graph is connected. So assume that it was a tree. Instead of a graph, it was a tree. Then we would have n minus 1 edges, and there will be only one path between every two pairs, right? Like if we choose any two vertices, there will be only one path. And that would happen if there were n minus 1 edges. If there are n minus 1 edges, it will always be a tree. Now there are n edges and the graph is still connected. So it is like you take a tree and then you just add one cycle somewhere. Now we have to calculate the total number of paths. So yeah, it is something like this. So definitely this information helps us that there are only n edges and not m edges, because if there were m edges, there will be like there can be a lot of strain paths, but it's not like that. It's just a single cycle in the graph, and let's see how that will help us. So mm, okay, so there will be a single cycle in the graph, like I mean, let's say these are connected. So these three elements are in a cycle, and what's happening is that like when you go from here to any other vertex, instead of having one way to go there, you'll have two ways. So usually what happens is that, I mean, let me just draw this extra edge with some other color. So usually what happens is when you go from here till here, or from here till here, or any place, usually there's only one unique edge. But now, actually, only one unique path, right? Like if you want to go from here to here, there's only one path. But now there are two paths. You can go counterclockwise or you can go clockwise. So there are two paths instead of one path, and that's the only thing that will increase the count here. So any of these, whenever they go to any of these, instead of having just one path, they will have two paths. And same goes for this. Like any of these, if they want to go to any of these, instead of having just one path, they will have two paths. So that's how the cycle will affect. So let's take a bigger cycle. This one looks good. Okay. So like if there are four elements in the cycle, um, any path that starts here and goes beyond the cycle, uh, instead of having a single path, we will have exactly two paths. Okay. So let's see what we have to do here. Hmm. Okay. So one thing I'm thinking right now, what we can do is we can kind of merge this entire cycle into one vertex, one big vertex. After that, I think we just have to count how many. Wait a minute. Okay, so first of all, the first step will be definitely adding all the tree paths, and they are equal to NC2. Like we can pick any two elements, and we will get a unique path. So firstly, we'll add NC2. After that, we will make one cycle in the graph. And now we want to add all of the paths that involve at least one edge from this cycle. So for that, I'm thinking we can just merge this entire cycle. Then we can go to any element that is adjacent to this big cycle node, and we can count all of the paths that start here, go here. That will leave out these ones. Like obviously, we can do this also. Okay. So let's try to write what will be the answer. Hmm. For some vertex, let's say for this vertex, and let's assume, like, let's say for this vertex, and let's assume this had a subtree as well. So what will happen is all of these vertices, like the total size of this subtree, multiplied by, hmm, we go here, then we go here or here, one of these. Okay, so isn't it just the multiplication of this size into this size? Because this edge isn't actually present in the cycle, right? I'm just assuming that it's there. Sorry, this edge isn't actually present in the tree. Like when I will form the tree, I will make a spanning tree of the graph. It will leave one edge out. So we can calculate all of the subtree sizes, right? For this subtree, it's just the I'll just multiply this with this and this. Okay, that one seems fine. But what about this one? Let's say we had one here. So we will take the subtree of this size and we'll multiply it with what? Okay, it's easy. Like if we have to use this edge, then there are two paths, right? So we have to just see if using this edge is required or not. And if we have to use this edge, this will be the size of this subtree will be the answer. This subtree is excluding this edge, obviously. So the same thing we have to do everywhere. Like let's say we had a subtree here, we'll just uh, if we don't use this edge, then the size of this subtree should be multiplied to this. So what will actually happen is we will multiply the size of this to this and everything. Actually, we can even leave this. We can directly take this vertex because even these paths are doubled, right? So we just have to consider all of these vertices, and the total number of that if we call the size of this subtree s, then we just have to multiply s with this size. And if we call this s, then we have to multiply s with this and this. Okay, so only for LCA it will be a little problematic. Oh, but wait, what if it was like this? Now, what will we do here? Which paths will be doubled? Hmm. Now I think okay, now there's a lot of redundancy because we have to leave this out while multiplying. Let's see. So we will have to take all of the elements connected to this vertex, okay, and we will take this size like without using these edges, the cycle edges. So I take the size of the subtree without using the cycle edges. Okay. Now what do I multiply this with? Mm, I definitely multiply it with this, right? Because here I didn't use this edge, so all of these paths will be there. And then I also multiply it with this one, because I mean if there was a subtree here, then all of them can go here or here. So from any vertex there will be at most two edges that are part of the cycle, and if I ignore those two, I just have to take the size of this and this the size of this and multiply it with the size of this and add it to the answer. This will give me everything twice. So in the end I'll just half it and this should work. Okay, so yes, let's try to figure out the rest as we are implementing this. Okay, so test cases n. The edges are also n, so we don't have to input anything else. Okay, let's call the edge xy. I have to store this edge somewhere, right? Okay. So right now I don't have the entire question figured out, but I have the central idea, and I'll figure out the rest as I proceed. So I have to clear the graph from the previous test case. Okay, now I have to add the edges to my graph. Are these division 3 contests getting a little tougher, or am I just getting dumber? Yeah, guess we'll never know. Anyway, so wait a minute, let me see something else. So how will I detect this cycle? If I mark the vertices visited, this will be the first. Okay, actually, there's another thing. If I make the DFS tree, then the only package will be to the ancestor. So that's another advantage. Like there are a lot of ways to form the tree. If I like any spanning tree algorithm, DFS, anything, or the any of the spanning tree algorithms I can use. But if I use DFS to form the tree, it will form a DFS tree, and the only package will be to the ancestor. So is this more advantageous in any way? Yes, it seems more advantageous because it will eliminate the case where we had to go over this LCA. In this, the LCA will have only one. So yeah, I think DFS forming the DFS tree is more advantageous here. So I form the DFS tree. Now what do I have to do? And I have some subtree here. Okay, I take this and I multiply it with this entire thing, this entire graph, except this. Okay, that's the first step. What do I do in the second step? In the second step, I'll take this. Okay, sorry, this was the edge. Let me pick another color. So in the second step, I'll take this and whatever subtree it has. I multiply this size with this entire thing, right? Also, if I don't multiply this with this, I'll automatically count each path once instead of twice. So whenever I go up a cycle edge, I just subtract the size. I'll just subtract the size, or I don't add the size here. Okay, so I think we need to perform one DFS to calculate the sizes, right? mark them unvisited. Visited is 0. Okay, now I need the sizes, right? S size, and size is also 0 now. Actually, size is 1, let's say. Now let's just start a DFS from the vertex 1 with no parent. Okay. Go to all of the adjacent ones. If it's equal to the parent, if x equal to parent, then I'll just continue because I don't consider the parentage. But if it's not equal to the parent and still x is visited, then this is the package. I don't know what to do about this yet, but must continue here. And then this is the rest. I will add the sizes, right? Size of z plus equal to size of x. I don't need this int, I will just take this void. And before doing this, I must calculate the size of x. That's e plus x. Okay, now I have all the sizes. And I think I know the package, but I don't have to store it because I can find it again in the same manner. Okay, so now I have all the sizes. Let's see what we can do now. I think I definitely need another DFS. So let's just copy this one. Okay, so after this one I have to mark them unvisited because I'm using the visited array. Okay, so first let me add NC2 to the answer. So n into n minus 1 by 2, this will definitely be in the answer apart from something else. Let me do this another way. Yeah, and I can keep a global variable for answer. Cool. So n into n minus 1 by 2 will always be in the answer, and then I will have to add something else based on the DFS2. Let's see what we have to do in DFS2. So again, I'll do this. That's the thing. And this has a package. So where will this package end? I think that will depend on the depth. So I should store the depths as well. Set these to 0. Depth of I is equal to 0. I should calculate the depths as well. So the depth of Z is maximum of I should send a variable here. I can just do this depth of Z equal to D. Okay, now I have all the depths. This can maybe return a value. So what should this return? This should return the highest point of the package. Depth of x. So this is the point where the cycle will end. Okay. Hmm. Okay, actually, I'm thinking of an alternate solution that might be easier. I'm not sure if it will work. Okay, no, that was wrong. So I have to continue this only. Anyway, so where was I? Yeah, like this is the maximum depth where this. Mm, so let me just keep a variable. I need an outside. Then return this. So okay, now I'm returning at which depth the cycle is ending. This is actually similar to finding those articulation points or something. Now I have to do this. Okay, so by the value of RET, I can determine if this belongs to the package or not. Okay, let's do this in 2 steps actually. Okay, cool. Mm, so let's talk about effective size. I think it would be advantageous to store the parents as well. So parent of z equal to p, and I don't have to clear it, I guess. That's fine, I don't have to clear it. So okay, actually I don't have to store it, I have it here in the DFI. What am I doing? Okay, so let's talk about effective size. Effective size is initially the size of z, but I have to subtract this one, right? So earlier I said that I will take the size of this and I will multiply it with this, and I will exclude this. That's what I said, right? But now I'm thinking, why don't I just multiply this with this and exclude this? Why is that wrong and why is this right? Are both of these wrong? Okay, I can do this. Yes, I can do this, but I will have to do something special for this one because like, this is not a part of that. Mm, yeah. So I can just multiply the effective size with the size of the. Okay. So I have effective size and size of mm, special vertex. Okay. So let's say this 0. Now right. If temp is not equal to, sorry, if temp is smaller equal to n, temp is smaller equal to depth of z, okay, then the size of special vertex is equal to the size of x, because then x is the special vertex, and effective size is equal to size of special vertex. I have to subtract this. Okay. So I got these two things. Now how do I use them? So first of all, if RET is smaller than depth of Z, so this is case B. Okay, I'm calling it case B, and case B is this. This is case B. Okay, and so what do we do in case B? Let's see. So I need size of parent minus the size of this parent vertex. Okay, this I will multiply with what will I multiply this with? The effective size. This is what I'm doing. Like this is parent minus z, and this is the effective size. So I'm multiplying these two, and like I'll have to add them to the answer. Okay. So this was the case B. And the good thing is this vertex also falls into case B, like all of these are in case B, because here also we will just multiply 1 with all of this, which is correct. And if we had some subtree here, we would multiply the size with this everything else. So that's correct. Okay, so all of these were case B. Now we have case A left. And let's call this case C. Case C is when for case C we don't do anything. Okay, so now we have to talk about case A. Okay, now if RET equal to depth of Z, so this is case A. Let's see what we have to add here. For this case A, I think we don't add anything here because um, we've done everything already. We're not multiplying with the children, right? So I think we're done. I think we don't have to do anything here. Because we multiplied this with this. Sorry, we multiplied this with this. Then we also multiplied um, what did we multiply? I think we multiplied 1 with this. Then we multiplied this with this. Now I don't think we have to do anything here. So for case A, we just do nothing. And that's it. So like I think we found the answer. Oh, I forgot to print it. I think I forgot to mark those visited, right? So visited 1 and visited is 1. This is wrong, right? Okay, this is wrong. And all of these answers are less than what we actually need. So I think we had to add something else. But this is a good thing because now we know some test cases where we're wrong. So I will just try to fix these. So let's see the first test case. I'll just draw the graph here. 1, 2, and 3. Okay, we have a simple cycle, and sorry. So we have 6 paths here according to the question. We have 3 into 2, we have 6 paths. Let's say we form the DFS3 something like this. Okay, and we have the package here. So what are we missing? First of all, we're multiplying this with 2. No, first of all, we're adding 3 to the answer. Okay. Then we're multiplying this with 2. So we're adding 2 again. Then what are we adding here? We multiplied 1 with 1 and added it here. And that did nothing else. So obviously it's 1 less than our answer. So let's see which path we didn't cover. So we covered these 2 paths, okay. Then we covered this path as well. Which path did we miss? Covered this. I covered these 2. Oh, I think I didn't cover this path. No, I covered it here, right? I covered this and this. So I've done all the paths involving 3. Did I cover all the ones involving 2? I did this. I didn't do this. No, again I did it here. Oh no, wait. 3 plus 2 plus 1 is equal to 6, so that should have been correct. What did I miss? In the beginning I had 3 and into n minus 1 by 2. Okay. And then I took this and multiplied it with this. I'm doing something wrong. Should this be n minus size of z? Okay. If it works, I think I should submit. Even if it's wrong. Oh my god, I wasted a lot of time. I said I'll finish it in 1 hour, but it's been, I don't know, 1 hour 20 minutes. And I think this is wrong as well. Oh, it's accepted. So I won't be attempting F. I mean, if I do, I might be able to solve it, but that will waste a lot of time for me and I have other things to do. So I'm gonna end this video here, and please like and subscribe to my channel. And but if you don't speak Hindi, I think I won't advise you to subscribe it right now, because like I'm not doing a lot of English content right now. And if I but like keep watching. If I someday decide to do a series of English content, or permanently moving towards English content, I'll write a post or make a video about it. So yeah, keep a close eye if you like my content. And yeah, so if you think the video was helpful, share it with someone, and peace out.